The second way of finding roots by the iterative methods is Newton's method. And Newton's method gives a much more accurate approximation of the roots. It uses calculus. And basically, what happens is if we look at the curve that's given here, there's the curve, and the root is being pointed out there. Now, if I take another point, if I take another point A, and I find the tangent at A, which goes down there, if I find the intersection of that tangent, where it crosses the x-axis, then my A1 is the approximation to the root. So I'll just say that again. We've got the curve. We take a point, and we're given a point in every question, A. We find the equation of that tangent and where it intersects with the x-axis. And the intersection of that point is our new approximation to the root. So you can see here A1 is closer than the first point we took A. So you don't have to worry about finding the equation of that tangent there. We have a formula, and the formula is written down here. So to find the location of A1, we take A minus f of A over f dashes of A. So we've got to find the derivative of the function. So question 1 is written above. You can write this example down. And it shows that this function has a root between x equals 0, x equals 1, and then use one application of Newton's method to find that approximation. So part A, to show a polynomial has a root, we just need to show that between these 2 points, one of them is positive and one of them is negative when we sub in the function. So the factor that it's 0 here means we're finding the root. That's f of x, and we're making y equals 0. So I'm going to write it as f of x equals x to the half plus x minus 1. And I'm going to find f of 0 and f of 1 and hope that they have different signs, because then there's a root in between it. So 0 to the half plus 0 minus 1 equals negative 1. So that's less than 0. So I'm assuming that f of 1 has a positive sign. So it's 1 to the half plus 1 minus 1, and that's 1. So that's bigger than 0. Therefore, a root exists between x equals 0 and x equals 1. And all you've got to do to show that is that they've got different signs. Okay, and part B. So we're going to write down the formula for Newton's method, which is A1 equals A minus f of A on f dash of A. Make sure you get that formula right. The derivative's on the bottom. So we start with the function and we derive it. That's the way I remember it. Now, this is an interesting question. They don't actually give you a value for A. So you have to choose. You've got to choose between 0, whoops, didn't function that. You've got to choose between 0 and 1. Now this is unusual. Normally they do give you a value. So it's best to go and find the derivative first and see if it works. Okay, and in this case it actually doesn't because you have a 0. So if I find the derivative, so I know what f of x is up there, f dash x equals, swing the half to the front, put down the x and reduce it by 1 plus 1. Now if I write that without the indices, f dash x equals a half, and that is 1 over root x plus 1. And if I fix that first fraction up, that's 1 over 2 root x plus 1. Now, if you think about subbing 0 into that, which is one of your choices, you can't have a 0 down the bottom. So in this case, we have to take the 1. But this is a strange question. Ordinarily, they give it to you, but they don't have to. So that's what you do in future. Find f of x. And then if f dash x works, you can use whichever one. that you wanted to. Just something else I wanted to point out was that when we subbed in f of 0, we got -1, and when we subbed in f of 1, we got +1. Now, I say that the number's not important, but it means that the root is probably symmetrically between them, or kind of, sort of. So at 0 it's -1, and at 1 it's 1. So it's evenly spread between the two. So if 0 worked in the derivative, then it wouldn't matter which one you took because they are quite evenly placed. But let's take 1 for the moment. So if I write my Newton's method out again, it's that A1 new root equals A minus f of A on f dash A. Now I think we've found all the values of these. We're going to take 1 as our root. F of 1 was 1, and f dash 1, I'm not sure we've figured that one out yet. So f dash 1 we'll do up here next to f of x is 1 on 2 root 1 plus 1, which is 1.5, or 3 on 2. So it's 1 over 3 on 2. So if I sort that out, that's 1 minus 2 on 3, which is a third. So our new root, if we draw this again, we knew it was between 0 and 1. 0 was a minus, 1 was a positive, and it's come out that it's somewhere around a third. Not exactly, but that's our new approximation for the root. If they ask us to take another application of Newton's method, then this is our new way. This is what we'd be subbing in to here and here and here.